Hello everyone, welcome back. In this video, we're going to look at the derivatives of exponential and logarithmic functions. Now back in chapter 1, we defined the number e, which was approximately 2.7. And now we'll look at the reason why we defined this number e. If we were to look at every possible exponential function of the form y equals a to the x, then the function where y is equal to e to the power of x is the only one where the tangent line at the y-intercept has a slope of 1. And so if we were to look at the definition of the derivative at the point where x equals 1 and the function f of x equals e to the x, then the following limit is given here. So the derivative at 0, which is the limit of e to the h minus 1 all over h as h approaches 0, is equal to 1. Now this will be very useful for calculating the derivatives of exponential functions. And again, we'll leave the proofs for these in another video. So now we can look at the derivatives of the exponential functions. So first we'll look at the derivative of the natural exponential function, e to the x. And it turns out that the derivative of e to the x is itself. And it's the only function that has this property where it is equal to its own derivative. And so what this means is that the slope of the tangent line to the curve, y equals e to the x, will be equal to the y-coordinate of the point. And so now we can look at the derivative of the exponential function in general. So the derivative of a to the power of x is equal to a to the power of x times the natural log of a. And so this also works in the case of the natural exponential function, right? If we apply the rule to e to the power of x, then this is itself, which is e to the power of x, times the natural log of e. And we know that the natural log of e is equal to 1. And so this can be simplified to e to the x times 1, which is e to the x. Now we'll also look at the derivatives of the logarithmic functions. So we'll start with the natural logarithm. So the derivative of the natural log of x is equal to the reciprocal function, which is 1 over x. And in general, the derivative of any logarithmic function with base a, so log base a of x, will be equal to 1 over x times the natural log of a. And again, if you apply this general formula in the case of the natural logarithm, you would get 1 over x times the natural log of e. And once again, the natural log of e is 1, and so that will be simplified to 1 over x. Now the proofs for these formulas will require us to look at methods, which we will develop in the next section. But we've stated all of the derivatives here just to complete our list of derivatives. So now let's have a look at some examples of using these rules for log and exponential functions. So in the first example, we have y equals 2 to the power of x. So we have an exponential function where the base is 2. So if we look at applying the derivative of the exponential function, this will be equal to itself, which is 2 to the power of x, times the natural log of the base, so the natural log of 2. In the next example, we have log base 2 of x. So now applying the derivative of log base 2 of x, we have 1 over x times the natural log of 2. In the third example, we have x to the power of 4 times e to the x. And so here we have a product of two functions, and so we will look at using the product rule. So we will call x to the power 4 as f, and e to the x as our g. And so using the product rule, we have 4x cubed times e to the x plus x to the power 4 times the derivative of e to the x, which is e to the x. Now in the fourth example, we have x plus 1 over 3 to the power of x. So we will need the quotient rule. And so we have the derivative of x plus 1, which is 1, times 3 to the power of x, minus x plus 1 times the derivative of 3 to the x. So we have an exponential function. So that is 3 to the power of x times the natural log of 3, all over 3 to the power of x squared And so here we can simplify. In the numerator, we have a common factor of 3 to the x. So we can factor out 3 to the x. We then have 1 minus x plus 1 times the natural log of 3. And this is all over 3 to the x squared. So now we can cancel one factor of 3 to the x. And so we are left with 1 minus x plus 1 times the natural log of 3, all over 3 to the x. In letter E, we have y equals x times the natural log of x. So here we apply the product rule. So f is x, and g will be the natural log of x. And so the derivative using the product rule is 1 times the natural log of x plus x times the derivative of natural log of x, which is 1 over x. So we can simplify this to the natural log of x. In the second term, we can cancel out a factor of x. So we're left with plus 1. Letter F, we have y equals 4 to the x over cotangent of x. And so here we will apply the quotient rule. So derivative of 4 to the x is 4 to the x times the natural log of 4, and that will be multiplied by cotangent of x, minus 4 to the x times the derivative of cotangent, which is negative cosecant squared. And this is all divided by cotangent of x squared. So here we can factor out a common factor of 4 to the power of x, and we're left with the natural log of 4 times cotangent of x plus cosecant squared x, and this is all over cotangent squared of x. In letter G, we have y equals x times the sine of x times e to the power of x. And so now in this case, what we have are three different functions. So we'll call this f, g, and h. And we have multiplication, and so we need to apply the product rule to three functions. Now the product rule for two functions was f prime times g plus f times g prime. So now, how can we generalize the product rule to three or more functions? So what would the product rule look like if we wanted to differentiate the function f times g times h? Well, if you might have guessed, what we could do is take the derivative of each function separately, and then we multiply it by the other two functions. And then we add all of these together. And so what this would look like is, what we would have is f prime times g times h plus f times g prime times h plus f times g times h prime. And so we differentiate each function separately, then multiply it by the other two, and then add all of these together. So let's apply this rule to our function, x times sine x times e to the x. So f prime is 1. That's multiplied by the sine of x times e to the power of x. And then we add it to f, which is x, times the derivative of g, which is cosine of x, times e to the power of x. And then lastly, we have f times g, so x times sine of x, multiplied by the derivative of h, which is e to the x. And so if you want, you can factor out a common factor of e to the x out of all three terms, and we're left with the sine of x plus x times cos of x plus x times the sine of x. In letter H, we have y equals the natural log of x divided by x squared times the cosine of x. So we have a quotient of functions. We also have multiplication in the denominator. And so for this function, we will need to apply the quotient rule. And then while we're applying the quotient rule, there's going to be the product rule. So when we differentiate the denominator, we will also need to use the product rule. So let's call the natural log of x as our f, and x squared times cosine of x as our g for using the quotient rule. So the quotient rule says to differentiate f, so the derivative of the natural log is 1 over x. This is multiplied by g, which is x squared times the cosine of x. And then we subtract f, which is the natural log of x, and then we multiply that by the derivative of g. And the derivative of g, we need to apply the product rule to x squared and cos of x. So we differentiate x squared, which is 2x, then we multiply it by the cosine of x, and then we add it to x squared times the derivative of cos, which is negative sine. and this is all divided by the denominator squared, so x squared times cos all squared. Okay, so now let's simplify. So we have 1 over x times x squared. We can simplify this to an x in the numerator. And so we're left with x times cosine of x minus. So let's also distribute the negative natural log of x through the square brackets. So this would give us minus 2 times x times the natural log of x times cosine of x. And then we have plus x squared times the natural log of x times the sine of x. And this is all over x squared times cos of x squared. So we can apply the power to both the functions. So this would be x to the 4 times cos squared of x. In letter I, we have y equals x times the tangent of x over log base 3 of x. So here we apply the quotient rule, and while applying the quotient rule, we will also need to use the product rule. So using the quotient rule, we need to find f prime of x. So f prime is the derivative of x times the tangent of x. And so we need to use the product rule on x times tangent of x. So this would be 1 times the tangent of x plus x times the derivative of tan, which is secant squared of x. And this is multiplied by the log base 3 of x. And then we subtract x times tangent of x multiplied by the derivative of g. So the derivative of log base 3 of x is 1 over x times the natural log of 3. Okay, and that is all over the denominator squared, so log base 3 of x squared. So now we can simplify. So we will distribute the log base 3 of x through the brackets. And we can simplify the x's in the other term. So this x and this x can cancel. So we are left with tangent of x, log base 3 of x, plus x secant squared x log base 3 of x minus tangent of x divided by the natural log of 3, and this is all over log base 3 of x squared. And in the last example, we have 1 minus e to the x times secant of x, natural log of x, plus 1. So here we need to apply the product rule. So we will call 1 minus e to the x as our f, and secant x times the natural log of x plus 1 is our g. Now for this function, we will need to apply yet another product rule as we apply the first product rule. So when we differentiate the function g, we will need to use yet another product rule. So the product rule says we differentiate f, so the derivative of 1, which is 0, minus e to the power of x, since the derivative of e to the x is itself. We multiply this by g, which is secant of x times the natural log of x plus 1. And then we add it to f, which is 1 minus e to the x, multiplied by g prime. So the derivative of secant x times the natural log of x. So we apply yet another product rule. So we can call secant of x as f, and the natural log of x will be our g. So applying the product rule to those two functions, the derivative of secant x is secant x times tangent of x. That's multiplied by the natural log of x. And then we add it to secant of x times the derivative of the ln of x, which is 1 over x. And then we add it to the derivative of 1, which we know to be 0. And so this is our derivative. Okay, and if you want, you can expand out the terms, but we will leave it as this for now.